All right. Good afternoon, everyone. Welcome back to our seminar series on optimization, algebra, and geometry. Today we are very pleased to have Professor Wutang Wang from University of Wisconsin-Madison. Wutang is going to talk about topological aspects in algebraic optimization. Thank you.
Okay, thank you. Thank you for the invitation. Today I just want to give like an overview or survey of like a series of work where we try to understand, in some sense, the complexity of algebraic optimization problem and how to relate the complexity with the topology of the varieties. Okay. So what is the optimization problem? Optimization problem is basically we want to find the maximum or minimum value of a function on a space. And so our method will be limited to the case where f, the function f, and the model space are algebraic varieties. Okay, because yeah, the method we use are highly like algebraic geometric. For transcendental objects, most likely they will not apply. And so what is the algebraic degree of an optimization problem? So it's basically there are different methods to solve an optimization problem. And in the algebraic geometric way to find to solve an optimization problem is you find the critical points of the function on the space. You find all critical points of the function on the space over the field of complex numbers. There will be finite many critical points if your data or if the function f is somehow general. And then you check which of the critical points are actually real. And among the real points, you evaluate and you find the maximum or minimum. So the complexity of this approach is essentially measured by the number of critical points of the complexified function on the complexified space. Okay. So here, really you have to complexify everything and consider complex algebraic varieties. Over the reals, things just behave because real number is not an algebraic closed field. Things will behave pretty bad in many ways. So make things easier, we should work over the field of complex numbers. Okay, and throughout this talk, we will kind of focus on two kinds of examples, and the examples turns out to be of different nature. We have to kind of handle them with quite different technique. Maybe not different techniques, with different kind of method of calculation. The essential ideas are similar, but the presentation turns out to be kind of different. One type of problem is the maximum likelihood estimation, where the function f is like a power function, is like each coordinate to a general power. The other one is the closest point problem, or a linear optimization problem on algebraic variety. I know that the word linear optimization may mean different things, but for us, we are just considering. By linear optimization, we are just optimizing a linear function. Okay, so that's the case where f is a linear function, and a variant of this linear function is the Euclidean distance function, which corresponds to the closest point problem. I'll explain in a little more detail how the linear optimization and the closest point problems are related.
And sorry, is there any genericity condition here? Because you said the number of critical points, so it could be infinitely many, right?
Yeah, it could be infinite. Yeah, so you assume the data point is generic. So the likelihood function or the closest point, the point you choose, like from which you measure distance, should be generic to make sure that you have the genericity condition. Okay. Yeah, feel free to ask any questions. Okay, so let's kind of explain a little bit how topology comes in. Let's start with the example of maximum likelihood estimation. And we define this the algebraic degree of this maximum likelihood of optimization or maximum likelihood estimation on a variety X, which is equal to the number of critical points of this likelihood function restricted to X, where UI is supposed to be general. And when I say critical points, so in general, X could be singular. In that case, I only look at critical points along the smooth locus. It's in fact possible to define what is a critical point. So when you have a critical point on the singular locus, but somehow the generality condition guarantees that all critical points will occur on the smooth locus. So for us, we can assume, we can define the critical points. We can only worry about critical points on smooth locus. Okay. And the number of critical points is defined to be the maximum likelihood degree of a variety. And one example is if your X is the whole space. So this is like the unobstructed maximum likelihood estimation. Then you always have a unique solution, right? This is correspond to the fact that ML degree equals 1 if there is no constraint. But if you have some constraint, like for example, if the ambient space is 2-dimensional and you have a curve inside the 2-dimensional space, if X is a curve in C2, and if it's a general curve of degree D, this is an easy calculation that the maximum likelihood degree depends on the degree D. And you can see the more complicated the curve is, the higher the maximum likelihood degree will be. Okay. So now we come to, and actually the previous example is computed using this theorem of Junha. Junha says, well, on one hand side, you are computing how many critical points the function have. And in fact, it has a perfect topological interpretation, which up to a sign is equal to the Euler characteristic of the variety X, where X is defined to be the affine variety in Cn. But you have to remove the coordinate planes because these are like, right, when you think of the maximum likelihood estimation, you are really your critical point should not be like on the coordinate plane. So you should really like remove the coordinate plane from your variety, and also this hyperplane which corresponds to the sum of the variables equals 1. You remove them, and these are exactly the right where this kind of functions vanishes. You kind of want to exclude them, and then compute Euler characteristic. That's it. Very nice, very clean formula. And the proof uses some kind of intersection theory. Alufi's kind of work on Chern-Schwarz-McPherson classes. Yeah, it's a little complicated because this whole Chern-Schwarz-McPherson classes some kind of relatively deeper theory in intersection theory. But later, I joined with Yongqiang Liu and Laurentiu Maxim. We kind of gave a much simpler, or much more elementary proof, which only kind of used the elementary Morse theory. Which we reprove this equality using more elementary Morse theory, and we prove that this space on the right hand side you are computing Euler characteristic is homotopy equivalent to a fiber bound over a circle with some cells of dimension X attached, and the number of cells is equal to ML degree. And this is a very good example where Morse theory is a theory that relates critical points with topology, right? And on the right hand side, exactly it's topology. Left hand side is exactly critical points. So you can imagine Morse theory is the right thing to apply. And the Chern formula only applies for smooth subvarieties. But if X is singular, there is also then the standard Morse theory wouldn't work. You have to use a little more advanced, either like stratified Morse theory or some kind of intersection theory to give a more. I mean, the formula will be a more more complicated form, which I don't want to write down. But basically, there is a formula for a general X, where the right hand side will not just be one Euler characteristic; it will be a weighted sum of Euler characteristics, where you have to kind of include the singular strata and how the singularity behaves along, like you have to like involve a Wien stratification. It's a little complicated, involving some singularity theory, but it's kind of in singularity world. It's some well established notion. It involves some standard notion in singularity theory. Let me see. Any question? Okay, that's the example of maximum likelihood degree. And next, let's talk about this Euclidean distance degree. So again, I start with an ifan variety X. But now instead of doing this maximum likelihood function, I do this Euclidean distance function. This will be like a complexified square distance function. And the question is, I mean, if you want to find a closest point on the variety closest to a given point, you basically have to solve this question over the complex numbers and do what I said earlier, find what the real points and evaluate and so on. And then the question is, okay, then the question is can there be a topological formula to computing this Euclidean distance degree? Well, first, I want to kind of tweak the problem a little bit. I want to change the formulation of the problem without essentially changing the problem. So what I'm going to do is, I start with X in Cn. I'm going to embed X now in Cn plus 1 by using the previous coordinate function with one more coordinates, which is the sum of xi squares. And the claim is, I mean, this is kind of, if you think about it, this is almost obvious. The Euclidean distance degree. So basically, the critical points of this function is equal to the number of critical points of a general linear function in Cn now restricted to X. Right? Because what is this square distance function? You have the sum of squares, xi squares, and the sum of a general linear combination of linear terms. And the general linear function in the new n+1 dimensional affine space will look like a general linear combination of every coordinate. But then you can rescale, make the coordinate of this to be 1, then you are basically in the form of this function. Up to a constant. Of course, constant doesn't matter when you compute critical points. So this suggests that, or just to make the presentation simpler, we could just only think of this linear optimization degree or linear optimization, right? By embed X into a bigger dimensional space, I reduce the problem to a problem that I study the number of critical points of a general linear function, restriction of a general linear function on the affine variety X. So if I can solve this problem, then I solve the Euclidean distance degree problem, right? Because I'm just changing the embedding a little bit. Okay, not very much. Any question? Okay, if it's good, then let's move on. And then when it comes to this kind of counting critical points of a general linear function, this actually is something that's well known in the world of singularity theory. Okay, I didn't put years, but these are in the 2000s, okay, or maybe around 2010, or in the between 2000 and 2010. So it's somewhat, or even this kind of things. I mean, in some special case, I think it could trace even back to the 1980s. So the number of critical points of a general linear function restricted to x, okay, which we define to be the LO degree, is equal to the Euler characteristic of, no, it's not just x, but x remove a hyperplane. H is a general hyperplane, affine hyperplane. Again, you have to kind of, there will be a sign up to the -1 dimension. So once we have a topological formula for the LO degree, for the linear optimization degree, then using this twisted embedding, this will give us also a formula for the ED degree, Euclidean distance degree, which I will not write down, but it's very straightforward. And also, if x is singular, there is also a formula, topological formula. Also, the right-hand side will be more complicated. It will not be just a simple Euler characteristic, but it will be a weighted Euler characteristic, which involving a linear stratification. And the proofs of this theorem essentially use the Morse theory, the stratified Morse theory by Gorski McPherson, which were in around the 1980s. Okay, so what's the benefit of having such topological formulas? In some cases, I mean, Euler characteristic is kind of the easiest topological invariant that you can compute. For algebraic varieties, it's additive. Like if you take an algebraic variety, take a closed-up variety, take the complement, you know that the Euler characteristic of the whole variety is equal to Euler characteristic of the closed-up variety plus the Euler characteristic of the open, of the open part. So it's because it's additive, it's quite easy to calculate. It's much easier than if you want to calculate even the first Betti number of algebraic variety, second Betti number. So somehow the Euler characteristic, because it's additive, it's much easier to calculate than any of a specific Betti number. That's that's how I feel about it. And some consequences, because we have this topological formula, with the Jose Rodriguez, we could resolve a conjecture about maximum likelihood degree of rank 2 matrices of size 3 times n. And conjecturally, there is a simple formula. The formula was conjectured by Hansen, Rodriguez, and Servos. So in fact, we can compute. So we have iterated formula to compute the space of all rank 2 matrices of size m times n. But because it's iterated formula, the explicit formula gets complicated, or the iterated formula is somewhat simpler. So only for 3 times n, it has a simple form. And another consequence is we can use the linear optimization degree, which will, as I said, it will give us a topological formula for the Euclidean distance degree. We can use that to resolve a conjecture on the Euclidean distance degree of multi-view variety, okay, which occur when you perform when you use cameras to locate an object in 3-dimensional space. So this is a 3D triangulation problem. When you perform the 3D triangulation problem, you have to actually solve an optimization problem because the camera, so there is always error, and you want to kind of, out of the error, you want to find the best point in the space, kind of reflect the data from the pictures, and solving that optimization problem. So that optimization problem is the closest point problem of the on the multi-view variety, and we compute its Euclidean distance degree. I mean, the variety depends on how many cameras you choose. For n cameras, there is a multi-view variety, and we compute its ED degree is this as conjecture. Okay, that's the okay. Maybe before I move on, is there any question?
Yeah, I have one. So can we say anything about the real case based on this theorem by Jose and you? I mean, so this is for the complex case, right? So you have genericity and with complex entries. Does this upper bound, does this number imply any sort of upper bound for the real case?
Yeah, I mean, of course. So it will be upper bound for the real, but in general, the number of complex solutions will be much more than the real solutions. And it's complicated. So for the real, I mean, any of this topological formula will fail over the real. So you may ask, what if I only look at real solutions? Can I look at the real variety, take the order? I don't think anything close to that could hold. So over real, this is okay. I keep talking about this problem, Jose, and I mean, I think it's our approach would not be able to say anything about the real, and I don't see how one can like modify ours. It's quite rely on the fact that you have to work with.
Okay, thank you.
Yeah, I wish I could say something about the real, but unfortunately. Okay, so let's move on to something a little more recent and a little more refined. So when we perform the for example, for maximum likelihood estimation, people also study this maximum likelihood correspondence variety, in which you kind of put all the so you let U vary, and for each U you have some critical points, and you let U vary, and you consider like the universal family of critical points as U vary. Then as you vary, the locus of the critical points will form a subvariety. The subvariety will be in X cross C to the n+1. C to the n+1 is where U lives, right? So for every U, you have some critical points in X. For every U, you have some critical points in X. And now I put the U and X together. Okay, and the likelihood function is this. Okay, now this universal family of critical points is a subvariety in a product of affine spaces. When you have a variety in one affine space, you can define its degree. When you have a variety in a product of two affine spaces, you can define the so-called bidegree. And so the degree, how you define degree is you just project it to a general like affine space of the same dimension, and then of the dimension of the variety, you compute the degree of the projection. Now, what you do is the bidegree is gonna be like I n+1 minus I bidegree. So how you do it is you just project to a general product of Ci cross C n+1 minus I, because you know the variety of Mx is of dimension n+1. And for different choice of I, you will have different, I mean, you do a general projection, you compute its degree, it's gonna be the ith bidegree, or I comma n+1 minus I bidegree. If you change I, the bidegree will change it. So the bidegree is like a sequence of numbers. And we can also define a similar bidegree for linear optimization. You can define the linear optimization correspondence variety. It again lives in Cn cross, in that case, it's Cn cross Cn, and you compute this bidegree, which we call it LO bidegree, linear optimization bidegree, and the maximum likelihood we call it maximum likelihood bidegree. And they are generalizations of the usual maximum likelihood degree and LO degree, in the sense the zeros. So it's a sequence of number. The very first is actually the ML degree or LO degree. Because, for example, the ML degree is actually, you take the likelihood correspondence, you completely project the U factor. And the degree of that map corresponds to the choice of general U. You are measuring how many points lie above it, which is exactly how many Query points for that you have, and that's exactly the ML degree. So it's a generalization of the sense. And now there is a basic fact that for over a complex manifold, the Euler-characteristic. So what is the like higher generalization of Euler-characteristic? Is the Chern classes, because the degree of the top Chern class is Euler-characteristic for a complex manifold. But Chern classes has many terms. You have the zero Chern class, first Chern class, and up to the top Chern class. So then naturally you may wonder, is there some, since the bidegree in some sense is the deeper or refined measurement of the complexity, are they related to maybe the more refined topological invariant, which are the Chern classes? Okay. And the answer is yes. But okay. But it's the notion of Chern classes. It's easier if you work on a complex manifold, for example. Its Chern classes are easier. I mean, were understood by Chern and so on. Much more elementary. But now, because we are talking about affine varieties, they are not compact. And in general, X could also have singularities. That's also a problem. But thanks to the development, mostly due to McPherson and Gorski-McPherson. Okay, actually, yeah, for this one, maybe it's only due to McPherson. So what we can say is, given any affine variety, or given any like locally closed subvariety of X, locally closed subvariety of Pn, you can define so-called Chern-Mather class. Okay, it's some notion involves McPherson's very deep theory on his notion of Chern classes. Okay, let's not worry about this technical things, but the upshot is for ML degree. Okay, we start with the affine variety. And again, we have to remove all the coordinates. We have X circ. Then the Chern-Mather classes of this X circ is equal to, I think of it as a class in as a homology class or a child class on Pn. So because the homology class of Pn is the homology group is like Q, there is some Q. So given a total class here is like given a sequential number. And that sequence number again up to sign is exactly the ML bidegrees. And in fact, a special case of this theorem is actually due to Junha. Junha proved this assuming X is smooth and also is somehow transversal at infinity. So its intersections with the hyperplanes, the coordinate hyperplanes are transversal in some sense. In that case, this is actually proof. Yeah, maybe I should have put Junha's name there. And we have said that cohomologically, the top degree of Chern class is Euler-characteristic. But homologically, the zeroth degree is the Euler-characteristic. Okay, so if I look at what happens in the H lower zero component, remember B0 is the usual ML degree. So the right hand side up to sign gives us ML degree. And H0 of a Chern class is the Euler-characteristic. So that recovers the Euler-characteristic. So left hand side is the Euler-characteristic. Right hand side is the ML. So we recover the previous formula. So this demonstrates this is really a more refined identity. And for the LO bidegree, linear optimization bidegree, something similar happens. I start with the affine variety. In this case, I'm not gonna take anything away from the variety. So what I'm going to do is I'm going to actually take the Chern-Mather class of the whole variety. And the coefficient will not be exactly the LO by degrees, but it will be the LO by degrees after some linear transformation. Okay, you can imagine. So this identity is like a linear, so which says each BI is a linear combination of certain AIs by some, like there will be some like binomial coefficients. So basically AI and BI determines each other by some explicit formula. And you may wonder why in the ML degree case you have such simple formula, they are just AI, BI are just equal. And for the linear optimization degrees, they are not equal. They are related but not equal. So geometrically, this is related to the fact that the logarithmic cotangent bundle of C star and instead of Pn is a trivial, it's a rank n trivial bundle. But the logarithmic cotangent bundle of Cn instead of Pn is highly non-trivial. So somehow this kind of non-triviality is involved. Okay, I think I'm almost done, so I should be done in 2 or 3 minutes. So I have one more. This will be the last slide. So what are some of the applications? What does knowing the Chern class and so we know the Chern classes and the bidegrees are related. How can this help us? So the applications actually involve certain other class or other degree called sectional degree, sectional ML degree, maximum likelihood degree, or sectional linear optimization. They are defined by you just start with the variety. You take a section with the general affine linear space. You just cut the variety. Like by general hyperplanes a few times, you reduce the dimension of the variety, and then you take ML degree or linear optimization degree. Then right, depending on how many times you cut, you again get a sequence of numbers. So the one application is for ML degree, because these are also, we also have topological formula of the sectional ML degrees. So using both topological formulas, we can actually prove some relation between the sectional ML degree and the ML bidegrees. So there is a conjectural evolution formula. It's a little complicated. I will not write down the explicit formula, but basically the idea is they determine each other through some kind of like linear transformation, as we see in the previous theorem. They determine each other, and that was a conjecture by Junha and Sternfels, Sternfels. And for the LO case, there was a theorem. Okay, quite a few. It's 5-author theorem, which had established an equality between bidegree of projective conormal varieties and sectional LO degrees. And in fact, their result, first they assume the X is smooth. And also in their original theorem, they actually meet a transversality condition along infinity. So what we did was actually we could generalize their theorem to arbitrary varieties with arbitrary singularity. And we also demonstrate that some nice transversality condition should be there to make sure that equality actually holds. Okay. Again, I don't want to get into detail, but it's again we prove some conjecture. I mean, some kind of formula. Okay, that's my last slide. Thank you.
Right. Thank you, Botang. We have a few minutes for questions. Any question for Botang? So I actually have one. So why do we call the number of critical points algebraic degree? I mean, when I hear algebraic degree, I might think of the degree of Zariski closure of the image of the degree a function, right? Then what is the connection between right?
Yeah, what we call, for example, if I look at this correspondence variety.
Okay.
So this variety sits in here. If I project it to the second factor, So this variety is of dimension n+1 because its projection to the second factor is a generic finite, is a surjective and generic finite map. I mean, assuming the degree is the ML degree is not 0, and the ML degree is equal to the degree of the projection of the correspondence variety to this projection.
Mm-hmm.
So a lot of times this is how people compute things by computers. Somehow, one way to do it is you have a description of the likelihood correspondence variety, and you compute the degree of the projection. As I understand, in some cases you can compute the degree this way. In this sense, you can see it's really algebraic degree of a map.
Mm-hmm. All right, thank you. Any other question? All right, if not, let's thank Botong again, and thank you all for coming to our session. And hopefully, we don't have any talk next week due to Thanksgiving break, but hopefully I will see you the week after Thanksgiving break. Thank you very much and have a pleasant day.
Thank you.
So, Bhutan, are you gonna stay here? Or sure. Do you wanna leave or something? Okay. If you wanna have a break, like for a few minutes, that's fine. I can stay.
I'm fine. I'm fine. Yeah, I'm fine. Yeah, we can. Yeah, I would like to hear what you
Okay. Yeah. So if you want,
or maybe we can take a break. Let's take a 5 minutes break.
Okay. Yeah. Yeah. Have a good day.
Yeah. I'm too optimistic. Okay. Should I come back to the same link?
I will send you a Zoom link. Okay.
Okay.
Okay. Quickly, while hi, Botong. I have a quick question.
Sure.
This is Prasad.
Hi. Yeah. Nice to meet you.
It's unrelated to what you talked about. That's why I wasn't sure whether I should have.
Sure.
But there's a problem I thought of recently as I heard an ellipsoid fitting talk by a student from Harvard, and there was work of Pablo Parillo and others on this. So it's more about references. If you're familiar with any work on, given a bunch of points in RD, and you want to find somehow the best fitting ellipse, because the guys that looked at this problem, they wanted to know an exact ellipsoid fitting for the random instance. So they took some whatever Gaussian distribution or some distribution, and but so to me, they were interested in exact fitting because for some feasibility question of what they're looking at with STPs, that was more interesting. But to me, it was more interesting to study a least square version of it, right? Rather than fitting with a straight line, it's natural to fit with, why not some other curve and or some other body. So are you familiar with any literature on that kind of stuff?
I have not seen. I've not heard about. This is the first time I've heard about this problem.
Okay.
But I would. If I think of this problem, I would like to somehow make it explicit, right? What is the measurement of the distance? Like, how to measure which fitting is right? There should be a function measure how good the fitting is, and somehow. So I think it's somehow it could be related to the linear optimization kind of. Because again,
I think in one formulation it seemed like a quadratic optimization. So
quadratic. Okay. Yeah. So for quadratic optimization, the idea is you can always. So if you see this slides, let me show you this. So even for the Euclidean distance degree, there is also a quadratic term, and the idea is you kind of add those quadratic terms into your coordinate function. By doing that, you embed your variety X into or a set of points or something like that into a bigger affine space.
Okay.
And by doing that, you reduce the optimization to a linear optimization.
I see. Okay. So yeah, this is interesting. Yeah, actually, this is the slide when at which I was thinking, oh, I should ask him this question because of the sum of squares you have there. And so I'll ask Ali if it's not obvious on your website which paper I should look at, maybe for this formulation and related stuff.
Oh, this yeah, this is the I can, so this is the okay, I can, if you give me 1 minute, I can
Sorry, Ali, I'm if I'm
No,
keeping
that's fine.
the
No,
discussion.
this is part of the seminar.
yeah, I can send you the archive link. This
Okay,
is the
thank
the paper is this Euclidean distance degree of multi-view variety.
Euclidean distance degree. Yeah, of the mark. Okay.
Okay, sorry, I couldn't find the chat with the shares.
Yeah, no.
Yeah, it's right there.
Oh, got it. Okay. Thank you. Thank you very much.
Yeah.
Okay.
I'll
So,
take a look.
Okay.
all right.
Okay.
Thank you.
So,
Yeah.
okay, so I will see. I'll send you a Zoom link in a few minutes. Okay.
Thank
Thank you. Have a good day. Bye.
See you.
See you.